Hello, I hope you can all see my screen correctly. And welcome to this second session of Quantum in Practice. We're very happy to have QPERFECT with us for this 2-hour webinar today. I will just present briefly the organizers, and then I will give the floor to Ayman and QPERFECT. So this webinar is organized by TechUCI and CCFR, which are both parts of TerraTech. TechUCI is a TerraTech quantum computing initiative, which objectives are to develop the ecosystem, prepare skills, and identify use cases around the quantum computing and improve the understanding of programming models. To that purpose, TechUCI organizes seminars throughout the year. You can check out the program and also access past replays through the QR code on the screen. And we works at consolidating the ecosystem through projects with industrial members, such as this one, Quantum in Practice. So it's co-organized by CCFR, which is part of the EuroCC project and served at the French NCC among 36 centers in Europe. The objectives of CCFR are to connect industrials, academics, and public administration with the right resources, projects, and training opportunities. The aims at mapping key players so everyone can access the most relevant expertise in HPC, in AI, and quantum computing, of course. Our missions revolve around the various actions you see on the screen, with the constant goal of supporting you, always free of charge. Every action we do is totally free of charge. Let me just highlight our company support, which is personalized and tailored to each need. Examples, details, interviews are available on our website and YouTube channel to give you an overview of what we can offer and how we can help in the use of HPC and AI and quantum computing, of course, whatever the subject. So please contact us if you need. And let me tell you also a bit about our trainings. We organize 3 summer schools in HPC and quantum computing, and throughout the year you also have access to many webinars and trainings on various topics and levels. You can find the full list on our website, or you can connect on LinkedIn so you don't miss anything. Please connect to us. All sessions are recorded, such as today, so you can catch up anytime too on our YouTube channel. And just a quick information about the Grace Scott School 2026, which is a HPC summer school. The registrations are open, and you're very welcome to come on board and join us to this session, which will be 2 weeks, end of June and beginning of July. So this brings us to today's webinar. Quantum in Practice is dedicated to exploring tools and real-world applications for you to practice with today's quantum ecosystem. Each session features a leading quantum technology provider. Today we have QPERFECT. Please have a look at the agenda of the upcoming sessions, and we're sure we have various other sessions which will be organized end of June and beginning of September. So you just need to stay in touch so you'll have the full sessions. If you have any question, please use the chat. Everything will be answered. So don't hesitate to use the chat, as you cannot open your mic, but every question will be answered by Ayman, by his colleagues, so don't hesitate. Now it's time to give the floor to Ayman. Thank you for listening and enjoy your webinar.
Thank you so much, Marie. So I'll try first to share my screen. Can you please confirm that you can see my screen? Perfect. Thank you so much, Marie. Thanks again, TerraTech, CCFR, for the invitation and for allowing us to be here with you and talk about something we're very excited about, so profoundly love doing. So I think beforehand, before getting more into the presentation, I would love to present myself and all the other speakers. So I'm Ayman. I have a background in both physics and computer science, and today I'm a quantum application engineer. And I'll have with me both Maxime and Tom. Maxime is a software engineer here as well at QPERFECT, and Tom, he's doing his PhD there. I mean, within the research team. And each of us will try to tell you a bit more on either on quantum or what we do more here at QPERFECT. So this webinar structure would be really about, like, first, who are we? And we'll a bit introduce why emulators, and then we'll give you a quick introduction into MIMIQ, and then we'll get into the practicalities and more about traffic routing optimization, and end on the journey towards FTQC. So for this next part about who are we, I'll leave the floor to Philippe, our CEO. I'll let him introduce himself and tell you more about us.
Thanks a lot, Eman, and thanks a lot, everyone, to join this webinar. Thanks for the organizer. Eman gave me the opportunity to introduce QPERFECT in 5 minutes because you have a huge webinar on MIMIQ today and on quantum emulation. But just to tell you a few things I would like you to remember about us. First, we are a spin-off of the European Center for Quantum Science, which is in Strasbourg. So it's very important in the French ecosystem to acknowledge that there is know-how and laboratories working on quantum computing in Strasbourg. That's a center which has been investing already 50 million, which is quite particular for one thing, is developing his own public quantum computer based on neutral atom, 400 qubits, which will be delivered in the 2 coming years. And it is also part of the European Quantum Flagship Program, EUREKA, as we have 80 people working on, in theory, experimentation on neutral atoms. So we are a spin-off from 2023. We are quite rare. We get the Grand Prix iLab the year of the inception. I don't know if there is other deeptech which is getting this prize the year of inception. We are quite known, I hope, now with you onboarding the webinar, known for MIMIQ, which has been launched now more than 1 year ago, and very efficient in all the different benchmark that MIMIQ has been participating to, and you will hear about that. One of the big news for us in 2025 as a QPERFECT was to raise our first seed round of 2 million, but also to get a first project based on BTQ company working on one-shot signature cryptography algorithm, where we have the mission to port this algorithm in a FTQC mode on a neutral atom computing platform. And that's our focus for 2026 and 2027. Not leaving MIMIQ, of course. MIMIQ is part of it because it is a QPU we use now in order to have the first instruction and the first result for SS. BTQ Group has also decided to invest a bit more on QPERFECT and bought us on November 11, 2025. Just to give you the baseline on BTQ technologies, it's just to have all the value chain of cryptography. So first in the classical world, where we are implementing now in post-quantum cryptography, new algorithms certified from NIST, for instance, like Falcon, dilithium, etc., which make a hardware issue in terms of latency. So BTQ has a vertical product line on this with QSIM. They also launched a new layer of blockchain in order to answer the issues that Bitcoin, Ethereum, and all this kind of layer will face in the Web3 world. And the first mainnet will be available next July. That's what they call the quantum defense. But now they invest a lot on quantum offense. So not only using a quantum computer to hack a system or to decrypt a RSA algorithm, but also to propose new initiatives in terms of new algorithm, and the one-shot signature is the first one of them, but we could imagine many more to come, and we will announce new use cases this year at France Quantum or later in the year at Cannes Quantum World Event. So that's what we are very proud to be part of this full chain value chain. And regarding QPERFECT itself and our 3 core products, the first one, you know it. The first tier, Eman, perhaps next slide. The first tier is, I don't see the slide, Eman. Okay, just to refresh. So I don't have, here, perfect. So MIMIQ, which is a subject of what you are going to talk with Maxime and Tom and Eman today. So high scale emulation, in order to try to improve how your algorithm may run one day on the quantum machines, but also to start to understand the noise model of the machine you are going to use, and how we compile this in order to be more effective on the FTQC mode. So that's why you will hear more and more regarding QPERFECT about the quantum logical unit, which is a new layer in our software stack. And that's something that we put a lot of effort, because as you also understand, quantum error correction is something very important to consider and to manage very well. So we have a dedicated team of 6-7 people working only on that. And that's all for me. That's what I wanted you to remember. I want to thank you as the organizer. I hope you will have a wonderful journey. If anything I've said is also interesting for you, feel free to come to Eman after this webinar. But first, let's start with MIMIQ and all the wonderful things that you can do with this product. Thanks you to all of you.
Thank you, Philippe, for this quite interesting introduction about MIMIQ. So now the question is, why actually do we need emulators? Why can't we go straight away to quantum computers? And in order to answer this question, I'll invite to the floor my colleague Maxime to tell you more about this part.
Thank you, Ayman. I hope you can all hear me well. Nice. So before we start with the practice on MIMIQ, we need to set a few things. First, we want to share a little bit of the context of why we need emulators, and also a little bit of the theory that will be necessary before we start the practice, because we are still doing quantum computing. It is necessary. So why emulators? One number we like to give to people is the one regarding error rates on quantum computers. So you might have heard a few times that quantum computers today are very prone to errors, are very noisy, but it's nice to have an actual idea of the numbers behind it. On this slide, you can see that on a classical computer, you get 1 error on average every more than 1 billion operations. It's a very low number of errors, whereas on a quantum computer, you will get 1 error every 1,000 operations. So to actually develop a full application, an algorithm on a quantum computer today is a little bit complicated, because you won't get the result you expect. For this, you will need to add some error correction layers on top of it. And sadly, we don't have a quantum computer with a scale large enough to handle such a error correction scheme. So what you might want to do today is actually use an emulator to try to develop your algorithm first. This is what one of the offers we give with MIMIQ, is to actually start trying to develop some value around quantum, where you can develop some prototype for some FTQC quantum computer later, because we are assuming that at some point we will be able to just run any type of algorithm with a code correction layer on top of it, so that you can just focus on the algorithm itself without paying attention to the correction of errors. Today, you can do many things with the quantum emulators. Here is a list of some examples. First, you can benchmark actually quantum computers so that you can run algorithm on both a quantum computer and an emulator to check the difference in the fidelity, in the correct ratio of the results you get at the end of your computation. You can use an emulator to develop and test quantum algorithm, as well as quantum inspired algorithm to try to prepare for when a quantum computer will actually be available for everyone, which is the third point, actually. So that is the context. Now for a little bit of theory. If you are already knowledgeable in quantum, you know that a quantum computer is interesting because it can solve in a way the quantum many-body problem. By this, I mean that for each qubit that you have, if you add a new qubit to your quantum computer, you will need to add twice the number of complex number that you have to store to simulate the data. So for one qubit, with one qubit in a quantum computer, you can actually represent two complex numbers. With 2 qubits in a quantum computer, you can represent 4 complex numbers. For each new qubit you add, you can double this number. So with a very small number of qubits, you can actually hold a lot of data. That is the quantum many-body problem. And for n qubits, you can actually represent 2 to the power of n complex numbers. In quantum computing, we represent a quantum state using a quantum state vector, which is a simple vector of complex value, where each complex value is associated with one quantum state. I will go a little bit fast over these notions because I am assuming that you know at least a little bit about quantum computing. It is mostly a reminder of this theory. Once you have your state vector, you can evolve it, modify it to get the results you want using unitary matrices, which are simple matrices that respect the rules you can see on screen, that when you multiply it by its transposed version, you get an identity matrices. If you want to get the probability of measuring your state in a specific state, then you just have to get the norm. It's a squared norm of the amplitude in your state vector matching its state. So for example, C0 here represents the 0 state. So if you wanted to get the probability that your quantum state will give you this result, you just have to get the squared norm of this value. If you have multiple quantum systems, to add them up, you simply need to apply the tensor product between the different quantum states. In quantum computing, we like to work with gates. So at a very low level, an equivalent in classical computing will be to work directly with a bit instead of working at a very high level with Python, where on each bit you can apply logical gates such as AND, OR, or XOR. Here instead, you will have many other type of gates which have many interesting properties. What you can see on the screen here is that for each line, we represent one qubit state starting in the 0 state, and each box that you see will be one gate that will be applied on the qubit and will modify its output state. One box is a 1 qubit state. A box with a link and a point with it is a controlled gate, so that, for example, the first controlled Z gate will be controlled by the third qubit. As in, if the third qubit is in the 1 state, you will apply the Z gate on the first qubit. And at the very end, you can see a measure that will simply measure the qubit to collapse it in one of the states, 0 or 1. So this handsome pixelated man you can see here is Love Grover, a computer scientist that gave his name to one of the most famous algorithm, the Grover algorithm. We like this algorithm because it can show very easily one thing that quantum computing can do that a classical computer cannot do, simply. So imagine you have a database that is completely unordered. Here, for example, we have a list of boxes that are just in a line, so no structure to it, and one of the boxes is marked. A classical computer, to know what box is actually marked, will need to iterate over all of the boxes one by one until it finds the marked box, and then it will return the position of this box. In the worst case scenario, the classical computer will iterate over all of the box. So if you have n box, it will do n attempts to detect the marked box. But using the Grover algorithm, we actually can find this marked box with an algorithm that will work in the worst case scenario, square root of n times. So it won't have to check every box. It will be faster than this to find the marked box. Even though there is no structure, there is no way to follow from the lowest to bigger number, no alphabetic order. It simply can do this. So here is actually the algorithm we've seen so far is actually the Grover algorithm, or very easy version of it. And you can see that on each layer of gates, here you have the evolution of the state. instead of having a state vector, you just have one bar per complex value, or the probability of measuring the state here. You see that the Hadamard creates a superposition of all of the possible state from 0, 0, 0 to 1, 1, 1, meaning that you can measure with the same probability each of the states. We see that the oracle part of the algorithm will just simply change the phase, so from a plus value to a minus value for some of the state. And then the amplification part will simply increase the probability of measuring the marked state. We are going to see the algorithm in more detail. What I want you to understand here is that the state vector evolves when we apply the gate. That's all. Okay, so last few things on the state vector. A gate is actually a simple matrix. Here you have an example of how to apply a X matrix, which is the equivalent of a NOT matrix in classical computing on a quantum state. So you simply take the matrix of X and apply it, multiply it by the state vector. If you had a state vector representing 2 qubits instead of 1, what you will need to do is that you will need to do the tensor product between the matrix you want to apply and the identity gate before multiplying this matrix on the state vector. What you can see here is that the more qubits you have in your state vector, the bigger the matrices will be, and the harder the computation will be. There are many ways to optimize how you use a state vector and how you run a full simulation to run a quantum algorithm. But the only one I want to mention here today is that in MIMIQ, in particular, we make full use of single instruction, multiple data instructions, which is a way for us to optimize to the best of our capabilities how the state vector will run on one single CPU. It allows us to do some parallelization very efficiently with very little resources. But the state vector has some limits. As I've mentioned before, the more qubits you have, the more data you need to represent the quantum state. For each qubit, if you have n qubits, you will need 2 to the power of n complex numbers, which for the memory will increase drastically when you go over the 30 qubits mark. For example, for 32 qubits, you need at least 34 gigabytes of memory. And since each time you add 1 qubit, you have to double this number. For 40 qubits, it becomes 16 terabytes. And at some point, it becomes simply impossible to simulate because you simply cannot hold the full state. So what we do in QPERFECT is instead of focusing on the state vector, we are going to focus on another way to simulate and to represent the quantum state, which is the matrix product state. Here you have a more mathematical way to represent the state vector, where for each state you have a coefficient which matches this state. Instead, for the matrix product state, what we are going to do is that we are going to assign a matrix to each qubit, and this matrix will be modified depending on the value of the qubit it represents. What it means is that if I have a 2 qubit state, I will only need to hold 2 matrices, not more. If I have 20 qubits, I will need 20 matrices, not anything like 2 to the power of n. So there is one catch. If you have an entangled state, you will need to increase one of the dimensions of the matrices, which makes them grow. And that's with this size that we will be able to keep track of the full dimension, of the full entanglement, sorry. If you want to see it, we have another way to represent, a graphical way to represent MPS. We have a state, sorry, the first way is to represent a tensor network for the state vector is to have one box, so one tensor with the rank n, for n being the number of qubits. So one block with n legs. An MPS instead will be n blocks that are linked by one dimension. So as I've said before, if you have a very entangled state, you will have to increase the size of you will have to increase the bond dimension. So you will have to increase the size of the matrices, which also creates some limitation in this method. But we have a way to get around this problem. So the main method to reduce the size of MPS and the size of the matrices is to apply the SVD algorithm, which simply lets you take one tensor network and separate it into one matrix and one smaller tensor. If you do this repeatedly, you will be able to create just a train of matrices, so getting the MPS we've seen here. But what we can do also while doing this operation is truncate the values. So if we see that in the matrices we have very small values, we are just going to get rid of them. This is a very well-known algorithm, not specific to quantum. For example, we can actually represent one picture as a tensor network. Here we did it with the Cathedral of Strasbourg. And if you apply repeatedly the SVD algorithm on top of it, eventually you will be able to compress this picture. And what you can see on the picture is that even though you've compressed it by quite a lot, here 85% compressed, you can still see what is important about it. The most important data is preserved. And it is the same for the quantum state. Yes, we are going to compress it, but we are still going to be able to extract from it the most important information, what you want to measure at the end of your algorithm. One last detail, if you are using MPS, you usually want to use gates or multi-qubit gates that are closer together. So you don't want to use qubit 1 and qubit 25 if you can do the same with qubit 1 and qubit 2. It will be much faster to use closer qubits. It is just some optimization detail that might be important depending on your algorithm. So just to summarize, we have these two methods in MIMIQ, state vector in matrix product state. Usually you will want to use a state vector when you have few qubits, but a lot of gates, so a very in-depth algorithm. And you will want to use matrix product state when you have many qubits, like a very large number of qubits, but fewer gates, creating less entanglement. Okay, if you are interested in MIMIQ, here is a few more information. First, you can note that MIMIQ, or MPS particularly, but state vector also, is a universal simulator. By this, I mean that any gate can be run on it, but also many operations that are not unitary, such as the measurement, reset, or adding noise on top of it. We have the full state retention. So if you want to get access to the state, you have many ways to get it back. We have all-to-all connectivity. By this, I mean that you don't need to do only nearest neighbor gates. You can apply qubits from the qubit 1 to qubit 25 or whatever. Again, we have mid-circuit measurement and reset. So you can have this kind of workflow between the quantum state and the classical computing. It is very well optimized for CPU. We don't use GPU for this. And we have a lot of tools to do circuit optimization and preconditioning. I will give two examples of what we were able to do using MIMIQ. First is one implementation of a modified Grover algorithm, which we were able to use to get the prime number used in one RSA key. So back when we did this slide, the best quantum computer was able to factorize the number 21 into the 3 by 7 prime numbers, which is not a lot. Whereas using the algorithm on the state vector only, we were able to factorize the number 143 or 2086, or 2000 and something. What is important here is that using the state vector, the simulator, you are able to scale your algorithm a lot more than on quantum computer, where you can really only use it for a few qubits today. We also have a few examples of optimizations, and particularly one to solve the max cut problem using MIMIQ, which Ayman will partially show later in the day. And finally, a few benchmarks to show you what is the simulator able to do. So here you have, for example, a few simulations of 2000 qubits with a depth in gates of 64 that were able to be run with a limit of time in 300 seconds. Here is just a list of features that we support. The framework and the simulator is available in Python and Julia. We can do a C++ API on request. We have support for OpenQuasm, all of OpenQuasm 2, and some features are supported for OpenQuasm 3.
I'm sorry to interrupt, Maxime. I think the slides are frozen. Can you please just...
Oh, okay.
Ah, perfect. Oh, perfect. It's working now. Yes.
Okay. Thank you, Ayman. Okay. We have a lot of options to do some parametric circuits. So if you want to evolve a circuit depending on some parameters, we can do it. Again, you have matrix product state and a state vector. And everything you run using MIMIQ will be run on the cloud, on servers located in France. Oops. Okay. So how do we use it? For this, I will just show a notebook and do some live coding. So I hope you can see my terminal. First, what you want to do is to install the MIMIQ framework. So for this, I will create a Python environment. Okay. Oh, I had already one. That's fine. I will access this environment. Okay. And I will install MIMIQ circuits. It will take a few seconds. Very well. So here I am going to show how to create a very simple circuit and how to execute it using the remote service. Before actually doing this, what you want to do is to access the mimiq.qperfect.io website, where you will be able to see all of the logs for the simulations you are going to send to the remote service. I am assuming that you already have a QPERFECT account for this, if you want to follow along. You can also access the documentation at any time if you have doubt about how to use any of the API on the link docs.qperfect.io, where you have documentation for Julia and Python. Here we are going to focus on Python. Okay, back to the code. So in a new Python file, we are going to import everything from the MIMIQ circuits framework. Yes, I hope you can see well enough. To create a circuit, you simply need to create a variable and generate a circuit object. To apply the first gates on the circuit, you can use the push method, in which you will give the name of the gate you want to apply. Actually, here I'm going to apply a Hadamard gate and give it the index of the qubit you will want to target. The first qubit is 0 in Python. Okay, and you can always draw your circuit using the draw method. Okay, let's run it. A little bit too zoomed in. Okay, we can see fine. So here you have an example of a quantum circuit with only one Hadamard. Some shortcuts are very useful that we will use later, is to use a list of targets. So you can use range and give it 5 targets at once. So the qubit, 4 targets at once. The qubit 0, 1, 2, 3. And you can also add 2 qubits gate, as follows, by giving the control target and the actual qubit target. For clarification, we will just use 0 here. Okay, very well. You can also use ranges and list of targets for the 2 qubits gate for some shortcuts. Here we are going to use the 0 qubit as a control qubit and small error, and the 3 target in this list as the target qubit. So it duplicated the gate into 3 gates, always 0 as a control and the actual target in the list for the X target. And with this, you've already done one of the most simple circuit in quantum circuit, the equivalent in quantum computing, the equivalent of a hello world, which is a GIZ state. Now, we have a circuit. How do we execute it? For this, you will want to create a connection object to connect to the remote service. Okay? And using this object, you will want to connect. Once you are connected, you will use the connection object to submit a job to the remote service. The job is simply a circuit that you want to be simulated. Once you have the job requested, you can also request the results using the getResult method on which you give the job. So let's try this. When you try to connect, it will open up a login page where you can enter your ID and your password. Okay. Once it is done, you can close the page. I did it twice. And if you go back on the logs of the execution, you can now see that we have the new simulation that I've just tried that is already finished. So if I go back to my code, I will see that the results appeared. For this state, we've used the MIMIQ state vector, which took a few milliseconds to run. And in the results, we got the superposition of the 0 state and the 1 state that we have measured 1,000 times. One thing you want to do from here is, if you are only interested in either state vector or MPS, you can precise which algorithm you want to use by using algorithm equal either MPS or state vector. By default, it will call auto, which will try to run both at once and will give you the result of the first simulation that was finished. So just one example using MPS, we'll need to reconnect. There are ways to connect with a token so that you don't have to reconnect through the web API every time. And here you can see the same results, but we actually used the MPS simulator. If you know how to do this, you can already do quite a lot using Python. For the next part of the presentation, we are going to, of the introduction of MIMIQ, we are going to actually implement Grover, a very simple version of it, using another IDE. In QPERFECT, we are currently developing a specific IDE for MIMIQ circuits, which is still in development. But if you want to try it, you can do so by installing MIMIQ IDE, okay? And you can actually run or start the IDE by calling MIMIQ IDE. Oops. In this IDE, you have one section to enter code and one section to create a quantum circuit. If you want to play with it manually, you can simply take a gate and drop it on the circuit. For example, if I do so, it updated the code here and ran the simulation automatically. For this IDE, we are using a local simulator, so not the one on the remote service. So you won't need to connect every time. Just to finish showing the interface, in the histogram part, you have the result of the simulation. So using this circuit, we have only one qubit. So we have measured the one state 1,000 times. I will add one more gate so it's clearer, or one more qubit. Maybe Hadamar will be cleaner. Up. Okay, if we had a superposition, we could see it also in the result. And in the amplitude tab, you can see that we have a superposition of the state vector, the actual state, between the 1, 0 and the 1, 1 state. Below you have the actual probability of measuring each state, which is 50-50 here. So now we want to implement the Grover algorithm. First, what we want to do is to create a superposition. No, actually, okay, it will go to see the superposition. I don't know, 4. So let's imagine you have a superposition of the 4 first qubits. You will see the probability distribution as being shown here. One way to see this and to relate it to the Grover algorithm is to think about each bar as one slot of a database. For example, each part is one element of a database, and we are going to want to increase the probability of the bar that holds one specific value we are looking for. For example, let's say I want to find the value, I don't know, 1000. So here what I want to do is to increase the chance of retrieving this state. One other way to look at it is that imagine you have a bunch of doors in front of you, which are represented by one bar each. And behind the door, there is this number, a code that will help you for something, unlock, I don't know, a chest or something. You want to increase the chance of opening the right door and accessing the code you are looking for. So we need to start by superposition that we did. For simplicity of my code, I will just use bit string. You can ignore this detail for now. First, what we want to do is to mark the state that is interesting to us. So mark the 1000 state. This is the role of the oracle in the Grover algorithm. In our case, the oracle will take a bit string. It will generate a circuit that will use 1 qubit per element in the bit string, so len of bit str. Now, what we are going to do in quantum computing is very easy to mark the one state with a minus phase. So what we are going to try is to modify the 100 state so that it becomes the 111 state, and then it will be very easy to mark with a minus phase. For this, what we have to do is to iterate over the bit string, and if the value of the current element of the bit string is 0, then we are going to modify 0 to 1. By this I do using the X gate. Very well. Now, what will happen is that this state will become 1111. So to mark it, we are going to use the Z gate. We are actually going to use a controlled version of the Z gate that will be applied on all of the qubits. And for Pythonic reasons, we need the star here. Then we need to cancel the modification we did to the state. So do exactly what we did here. I missed one I. So exactly the same loop, right? On I. And this goes from one superposition to the same superposition with only one marked state. You can see it when we do this. So when we call append, we simply take the circuit that is given in parameter and add it to the original circuit. So here we have created this circuit, right? And you can see in the state vector, that the state we wanted to mark is marked, but the probability to retrieve the state is still the same. So if we execute the circuit, we still get basically every possible outcome. once the state is marked, what we want to do is to actually increase the probability of getting this result. For this, we are going to use the amplification or the diffusion part of the oracle of the Grover algorithm. And for simplicity, in MIMIQ, we provide some pre-implemented gates, which we call generalized gate, that allow you to just add a circuit directly into another circuit. So for example, we are going to take the circuit of the diffusion applied to the number of qubits we need, right? Which I did not define. Right. And we still need to tell it on which qubit it will be applied. So every qubit. And now what we have is the superposition, the oracle here, and then the diffusion operator that will increase the value of the state we marked. Okay, so good. Now we have almost 50% chance of getting the result we marked. So let's try to add the diffusion again. But no, it does not work because we've tried to apply the same gate twice in a row. They are both unitary gates, so they cancel each other. What we need to do actually is to remark the state before reapplying the diffusion operator. And then you can see that now we have 90% chance of getting the correct outcome. So good, but how do we know how many times we need to apply this sequence? Because if I do it again, I still get better result. But if I do it again, I'm starting to get lower results. So we already know how many times we want to apply this sequence. It's just by theory, we can look at it. Won't have time to get into it now. But the number of times we need to iterate over it is defined by the formula I need to get somewhere else. 1 second. Yes, here. Yes, so the number of times I need to apply this sequence is equal to this formula, which is pi divided by 4 multiplied by square root of 2 to the power of n. For this, I need numpy actually. Up. And this is nq, not n. So I can do for e in range maxitaire. And now you can see that no matter how many value you want in the outcome, you will always get the best possible result. 50 is not a lot. And yeah, a Grover algorithm at the end is simply a sequence of gates that you apply in a loop. So here you've seen that only using the push method and a few of the gates available in MIMIQ, you can already implement one of the well-known, the best-known algorithm in quantum computing. And I think it's already a good introduction to the MIMIQ framework. You will see that we are going to use a lot more features in the actual full notebook that Ayman will present, but this is already good to get started. Sorry, I'm seeing a question. Yes, for MPS, you want to use closed gates because of algorithmic reasons. It's not so much a hardware limitation. And yes, I think I will hand over to Ayman for the rest. Thank you for listening.
Thank you so much, Maxime. So that was quite an introduction. I think we can use a little break and we can answer questions for now. So please, if you have some questions, do not hesitate to send them using the chat.
Yes, so I am seeing a question, which is, does not the multi-control Z of the Grover's algorithm worsen the MPS performances? Don't you need to decompose the n qubit into several 2 adjacent qubit gates? Yes, it will be more efficient in most cases. However, in MIMIQ, if the decomposition is straightforward, we actually do it in the backend, so the user do not have to take it into account. It will be important to think about it if you have a very complex gate, such as the diffusion algorithm, which inside it has gates that are long distance. Then you will need to optimize the long distance inside this gate.
So let's get a bit more practical. In some sense, let's see what we can do with the MIMIQ, or let's talk about real problems in some sense. So today I'll be a bit onboarding you in one of the very famous classical problem around traffic routing optimization. And I chose to talk about something that is quite peculiar to the city where we're hosted. As Philippe said during the beginning, that QPERFECT is hosted at CESC, and we're in Strasbourg here in France. And what you may know already is that Strasbourg is very famous for its Christmas market, in the sense that the population of Strasbourg is around 300,000 people, but during the whole month of December, the population gets to 3 million people. And so the idea all the streets are very crowded. Everyone is so excited about visiting the supermarkets. And actually, this leads to two major problems that we can try to solve them, or that's at least what I'll try to explain, how to approach these two problems using MIMIQ or using Quantum in general. So this is a notebook that I'll be sending over after our meeting. So there's this notebook and there's a lot, so many other ones. Yes, so you have this Strasbourg.py, one about each problem classically, and then the quantum side, and then QUBO per se, QUBO. So there's a bunch of notebooks that you can actually work on during your free time, and if you feel that's something that is of interest to you. And I think the support team has sent you the identifiers and your email and password to get access to MIMIQ. And so actually you have access up until next week. So do not hesitate to spend some time in the upcoming days and discover whatever attracts you the most. And of course, if you have questions, even after the meeting, do not hesitate to reach out. So for this specific notebook, we are just importing it we're just importing the different packages we'll be needing. So I want to be running as we speak the code. I've run it before, but again, why not? You can do it when you have some time. You can run it as well. Okay, so as I was saying, Strasbourg Christmas market is one of the oldest Christmas markets in France. I think it dates to the 1500, and it's usually run at Place de Broglie here in the city center. And so today it hosts more than 300 wooden chalets. I didn't really double check all these details, but there's really a lot of things to see, and it's very beautiful, and you can do a lot of stuff. And today it's really spread out all over the city. So it's not only in Place Broglie, but it's in Grand Ile. And as I was saying before, there's an average of 2 to 3 millions of visitors per week. So there's a lot of monuments to visit. Okay, yeah, for this specific approach, or for this in this notebook, we'll only be focusing on 11 markets. But for instance, you can have 11 markets that you want to visit from all the let's say from all the city markets. There's 14 monuments that you want to visit as well, and you have one transportation option. So you can visit the Cathédrale, you can go to La Petite France, you can pick and choose. And of course you have to go to Place Kléber, the most famous one, where there's the very big Christmas tree. I think it's over 30 meters. And so the idea here is, like, what if a visitor comes to Strasbourg in order to visit these monuments and visit the markets, but wants to really optimize their time? They cannot stay in Strasbourg for the whole month, and they want to plan this whole trip in, let's say, 1 day or 2 days max. But for this, to approach the problem, we'll think about it. What if you want to visit these places once and for all and during the same day? So that's just the same map, but if we convert all the data that we can get from Google Maps, for instance, you have all the monuments represented as diamonds. You have the circles with colors. These are markets. And so the problem that I was trying to refer to is, first, the traveling salesman problem. The traveling salesman problem is when you have n sites, n monuments, n markets that you want to visit, and you're looking to find the shortest closed tour to visit every site and exactly once. That would mean that you can arrive at the train station of Strasbourg, and from there you want to do a round tour, visit all the markets or all the monuments, and go back to your original option. Classically speaking, we are looking at n-1 factorial of tours, and if we only care about one direction, then this will get divided by 2. And what you should know actually is that's an NP-hard problem in general, in the sense that no algorithm is known to find the optimum solution in polynomial complexity. in the sense that you can approximate, you can find some solutions that may work, but it's the complexity wise, it's really hard. And so that's briefly what's the traveling salesman problem. So here we're talking about the scenario, as I said, of someone who wants to visit different markets or monuments. And for the vehicle routing problem, here we're looking at the city of Strasbourg, for instance, has to give on a daily basis, needs to get all the merchandise from a depot. For example, let's say that the depot is at the train station, and every day they have to send three, like let's say bike courier, like three bike courier. They need to come to the market and they have to deliver some packages. And so the vehicle routing problem, it says that given n customers, so here we're talking about n markets, and you have a fleet of k vehicles. Let's imagine we have.
Ayman, we can't hear you anymore. I don't know if it's the same for everyone. Looks like it.
Yeah, the same.
Okay, they have connection issue. They're coming back. Just a few seconds, please.
Okay, Ayman is trying to reconnect. Once he joined, Marie, could you just give him the right to unmute himself?
Yes, of course. Ayman, you're back.
Thanks. Can you hear me now?
Yes, it's
Oh,
okay.
perfect. I'm sorry for this inconvenience. I'll try to share back my screen. Now you can see my screen. And so, as I was saying, the vehicle routing problem is when you have n markets and you have a k number of vehicles and you want to send a merchandise to these n customers, n markets, but you want to find an optimized way that they all visit every customer. I mean, you want to divide the n customers over the k vehicles that you have, and that for each vehicle, they will, overall, they'll be able to deliver what they have to deliver, and you want to minimize the total distance traveled. And so there is this, and so we'll be a bit diving into this multi-vehicle, travel salesman problem in order to make it more easy. So as I said, we can, as you can guess, we can already find a classical way, brute forcing stuff. You'll look into all the possible tours. For instance, here for the TSP, you want to visit the five markets, and you can go through classically brute force your way into looking at what are all the different possible tours, and then by the end choose which one is the most interesting one. For instance, if you want to go from Place Kléber and visit all these, the best option is to go on a round circle instead of, for example, going to Place Kléber to here and then go down and then go here, which you can already guess it's not very optimized. And for this toy example, let's say the best distance would be this one, averaging an average of 1,300 meters. So that's for the TSP, as I mentioned. And if we're looking at the vehicle routing problem, so imagine you have 5 customers and you have 3 vehicles. So the best way to approach this is to go from Gare Strasbourg for the first vehicle, to go from the Gare Strasbourg to Place de Broglie, to Place Kléber, and then go back to the depot. The second vehicle would have to go to the 2 beside Cathedral and the Place du Château. And for the last one to go to La Petite France and then come back. You can see here the itinerary. And that's actually one of the optimum solutions. But the question is, why does this get hard actually? So as we've seen here, if you have a small input, if you have 5 sites, if you have 5 markets, you have 24 distinct tours, which is trivial. A classical computer can manage it easily, no doubts on it. If we bump into 10 customers, which is still not big, the number of distinct tours gets to 360,000 tours, which is already too much for a human being to analyze, but still, with the classical computers that we have nowadays, it's still trivial. I want you to see that when I'm adding more and more markets, more and more sites, this number is growing very fast. And for 15 sites, we already have 87 billion tours, and that's still something that the HPCs nowadays can do. But if we get to 20, which is relatively still a small number, you get to 1.2 times 10 to the power of 17 tours, 100 quadrillion candidates. And so if you take a 3 gigahertz CPU evaluating one tour every nanosecond, it would need roughly 4 years to enumerate them all. Of course, there are other classical ways to solve this problem using heuristics, and that's actually what today big companies use in order to solve these kind of problems. But if we really are thinking about brute forcing our way into it, it gets very complicated and almost impossible. I mean, it gets at some point impossible to solve. And so here we have this small representation of the numbers that I've said before. So if you have n sites, then we're looking at the number of tours being, let's say, between 10 and 1,000. And this is scaling. And as I said, when you get to 13, this gets to over 10 to the power of 9. And this gray space, actually, it's when, I mean, where we think that quantum is becoming more relevant. Again, time-wise, here we have the number of sites, and here we have the estimated brute force time. If we're over 15 sites, we're talking about minutes. After, let's say, 17, 18 sites, we're talking about days. But once we surpass the 20, we can see that we are already reaching years. And so that's too much. And so the whole idea here is that this problem, we can translate it into a way that at some point a quantum computer can answer or do this compute differently. So first of all, we go from routing to QUBO. So when we are discussing routing, we're talking about discrete world, we're talking about different kind of inputs, different kind of data, and we need to be able to do or to translate this into QUBO in a sense that this problem should go into a discrete optimization problem. What I'm trying to solve, what I'm trying to say is that we need to be able to represent this as a function that we want to minimize. We either want to minimize the time that it's going to take. Sorry, I've seen someone said that. Can we zoom? So I'll try to zoom. So as I said, first we need to convert these discrete world data into data that a quantum computer could analyze. And first, we need to decide what's the optimization problem we're trying to solve. Are we trying to look into what's the minimum distance, or are we more interested into time? And what you should know also is that going through this conversion from the problem, as I stated before, into QUBO, it's a canonical interface language in the sense that you don't need to do this because you're using MIMIQ or because you want to use whatever architecture, but whatever you want, whatever actually backend you want to use, you need to be able to do this conversion. And for instance, the QAOA gate model can be used on MIMIQ. It can be used on other competitors. It could I mean also be used in different technologies or architecture in quantum annealing, for instance, and even some other problems that we can mention as such as VQE is actually using the same formulation. And so what I'm trying to say here is that we need to be able to convert this problem into a function that we want to minimize. Here I took if we take this function of x that has x1, x2, and x3, this function, when you compute it, you find different values. For instance, if we're at 0, 0, 0, then the energy is 0. And you can do the compute for all the other rows of this table. And so what I'm trying to say here is that we need to be able to encode the problem as a function, and the value of a function, here we refer to it as energy. It's the thing that we'll try to optimize or minimize. And one thing that you should take into consideration is that when we are, as in the classical world, when we're talking with a classical computer or the quantum computer, we usually encode data in 0 and 1. And that's actually something that we need to do here as well, to say that we have to pass through we have to be in a node or not. We have to be at some moment we are at this market or the other, and that's the first approach. But the problem is a quantum computer doesn't manage well zero and ones. It prefers -1 or +1. And that's what we usually refer to as the spin configuration. So that's nothing hard. We are just converting, or we are just going from this as our input data into -1 and +1. And that's through this very simple conversion. And so we can go from the first, we can go from this minimization into having a Hamiltonian, which is a function that represents the energy landscape. And so the point again here would be to minimize this Hamiltonian. And why am I referring to this? It's because you have a lot of already embedded functions in MIMIQ that allows you to return to find these HI, GI, and C prime. You can go from QUBO to Hamiltonian very easily, and it actually doesn't take you much. MIMIQ already does this for you. And to give you a glimpse, if we're talking about the TSP problem for 4 nodes, like imagine you want to visit four customers, 4 markets. This scales to 4 multiplies by 4, so 16 qubits. And converting the problem into QUBO gives us this matrix. That's quite technical, but that just to give you an idea what will be the output of this function used here. And so, as I explained, once we are able to go from the first, by the way, each section of this notebook has an independent notebook. So don't worry, when I'll send you the whole repo, you can find really details, answers to each section. And so what I was saying is that now we went from the classical problem, how we describe it, into this function that we want to try to minimize. And as I said before, that's the same Hamiltonian that we want to minimize. Okay, minimizing, that means that we want to find the best, the lowest energy, in the sense that this problem, if we go back to the classical example that we gave, we can see the problem as minimizing energy is minimizing the distance that we need to walk, or minimizing the time that the tour would take, for instance. And so I'm going to go a bit fast over these parts, but the idea is you can do all the embedding, and you can actually convert all of these into MIMIQ. And what the secret here, or what we're trying to do exactly, is to be able to get this into a circuit where we'll be able to have superposition to as we've seen with the circuit that Maxime has explained a bit before me, where we'll be trying to have our system in superposition to explore different pathways, and everything is about just doing some rotations with and tuning 2 parameters, and this actually optimization using a classical optimizer, in the sense that we'll have to do different boxes, like what we've seen with Maxime. He does the Grover to represent the we have to do it multiple times, and we just need to do it for here we chose p equals to 2. We will be doing it 2 times and see actually if it gets us any close to the solution or not. Let's get into an easy example. Okay, yeah, so what I was referring to is this is the Hamiltonian. This is how we build it, the same way as Maxime showed. We can specify to MIMIQ that you have a Hamiltonian, and then we can push the values for the parametric ansatz, or the different rotation that we'll be doing throughout the circuits, in order to look for the good solution, and then amplify it to have it as a result. And here, by the end, the whole point is to find the minimum value of h. As I said, to find the lowest distance, or to find the lowest time. Okay, and so when you do this, for example, here you need to connect to MIMIQ. You explain that you have to optimize the experiment. Here's the circuit. We're using theta and beta for optimization. And if you do it for, I don't, if I can show you. Okay, so we have okay, I should have skipped it. Okay, yes. Well, here we chose a toy example where we took a small circuit that you want to optimize. And the idea is that if you compute it classically, you would find that the best energy is minus 1.4. That's, sorry, theoretically, that's the value that we are looking to find. And when we did put this toy example, you'll find more details in the notebook, sorry. We find approximately the same, if not the same value actually, with a very basic error, and that used 30 iterations. And so a good figure to show this is that while we were putting different, while we were iterating over the circuit, the value of H did fluctuate. And after 5 iteration, we were already able to get the minimum energy. And so this minimum energy is, I mean, we can decode it into being the shortest path to explore for, I mean, the shortest path to explore, for example. I mean, okay, so Maxime briefly mentioned the max cut example. And so that's one way we can do to embed it in MIMIQ and then test it. And the idea is that when we have a max cut problem is we have 4 knots and we're wondering which 2 colors we should give in order to have the maximum cut. And here the classical optimum, we know it's to take two opposite knots and give them the same color. And so if we go through the program here, we found that that's exactly what MIMIQ says as well. And it gives us the same energy we were expecting from we had got from the classical solution. Again, this is always an iterative job. So always when we are, here in MaxCut, we can see that the Hamiltonian was fluctuating, and at some point you get to the final iteration. In this case, we knew that we had to take the same color for 2 opposite edges, so 1 and 1. Here it means that the first edge should have, let's say, green, red, or you should start with the first one being red, green, red, green. And so that's just a small example on how we can go from, let's say, we can go from a problem and then convert it into different layers, or in each step into having something that a quantum computer can understand, and then simulate using MIMIQ the best options and see the results. And so if you use the same thing on our small TSP and VRP, so here I chose the travel salesman problem with 4 markets. So we're trying to visit 4 markets. As I explained before, the matrix representing this needs 16 qubits. And so if you go through the whole conversion, we end up having, this job run into MIMIQ was able to give us that the best Hamiltonian is this one, and we were able to get it into 120 iteration. And for and I think a picture is worth a million words. And that what MIMIQ has given us in the results after the 120 layer, that's the decoded tour. It asks us to go from Place Kléber to here and there and here and there. You can already see that this is not the most optimized classical solution that you were able to find earlier, as the most optimized one would be a round circle. But actually, I had to stop this program, and that's why I didn't really leave it iterate too much to get to the most optimized version. But you can already see that the very optimum length would have been the 1,200 meter, and it was able to give us one that is 1,600 meter. So when doing the TSP for 4 we were able to get this optimum circuits. And if we go to the second one, to the VRP, so now we have a fleet that we want to deliver some packages. Here we have 3 customers, 3 markets that we need to deliver, and we have 2 vehicles. Here the number of qubits is nothing but we have 3 customers that we need to deliver to, and we have 2 vehicles, so we need n times n over k times k gets us 12. And so when we code everything, what we're able to see is that the decoded routes that was suggested by QUBO is that the first driver would only go to the first market, and the second driver could go to the 3 and 2. And that's the best way to visit 3, to deliver 3 customers if you have 2 vehicles. And that's actually almost the same as the classical optimum. There's no big difference. And here, for instance, we were able to get the same, or the best result, sorry. And so the idea here is that this is still small examples using here 12 qubits, but we can really push it a bit further. And the problem is, as Maxime was actually explaining about state vector, if you want to simulate this perfectly with a classical computer for n qubits generally, we already need 16 gigabytes of RAM. But if we want to go to, for n equals 40, we need 16 terabytes. And this scales exponentially. So this is getting high very fast. We cannot use state vector. And actually, state vector usually, if you run a job automatically, the state vector would be replaced by 15 to 20 qubits. Automatically, it would switch to MPS. And considering the fact that we can use MPS and that we can do a lot of approximation when running the TSP46, in the sense we want to visit 6 markets in one round tour, or 7, we can go from 36 qubits to 49 qubits. And what we were able to get is for different bond dimension. So when doing approximation at different scales, the fidelity changes. It gets better once you increase the bond dimension. However, the time needed is increasing as well, but still not growing exponentially. And so I figure as well. So here, when you're taking MPS fidelity over the bond dimension, you can see that when you increase bond dimension, the fidelity increases. When you are doing less, let's say, approximation, you are able to get better fidelity. And so it's all about finding this middle ground in some sense. And the time needed as well increases, as you can see in this figure. And that's for the TSP6 and the TSP7. Okay, so to conclude, of course, I'm sorry, I know that this has been maybe very fast. Of course, you have access to all these Jupyter notebooks and you can go in details. But the idea here is that in quite some code lines, we're able to have a clean and reusable pipeline where we can increase and adapt to our situation. We can see that for TSP7, we needed 49 qubits, and that's roughly 9 petabytes of RAM in state vector. If you want to simulate this perfectly, this would have taken a ginormous amount of RAM. And that's actually beyond the reach of any classical simulator. But using today a MPS, using MIMIQ, you can already find some results. And so this is curious. If you wanna scale to 10, TSP10 or TSP15, if you want to visit 15 markets, you need to get to 200 to 225. And so it's very interesting to test and see what you can do with this. And fidelity wise, if it's a trade-off that you can manage, then you can lower the bond dimension. You can get less fidelity, but you can get faster results and interesting possibilities. And so I'm stopping this sharing. I want to show you something else. And so before getting into, okay, so what I want to show you right now is something that was made possible thanks to Juliana from CRS4. Juliana is today one of our clients at QPerfect, and she kindly agreed, and you can find all the references to all her papers. But what I wanted to tell you actually is that what I described here has been a theoretical study about what how to solve the TPS problem. Juliana in her lab in CRS4 is doing this work actually, where they are taking depot location. So here they are they are working on a fleet optimization platform where they are taking depot location, customer addresses, delivery demands, traffic data provider, and so they are using real-time data services. So they have an idea about I'm sorry, I didn't mention it, but they are based in Cagliari, the capital of Sardinia in Italy. So, and they have a lot of, let's say, cameras or points where they get their input data. And so you have travel time API, you have live traffic conditions, you can see road closures, incidents, and so you have more and more constraints. They have all these data they have to manage. And so they use an HPC preprocessing to validate the data, to do some to do some computations, and they feed all of this into different quantum solvers, either QAOA, VQE, Grover, different solvers. I'm sorry. You can see it now. It was frozen. Okay, sorry. In case it was frozen, this is what I was describing. So we have a map. We have all the different routes that they're following, and using HPC and quantum MIMIQ, for instance, as a backend, they can try different ways to solve this same fleet optimization problem, and they use all of the data they collect in order to optimize and suggest the better or the best itinerary. So the idea here, it's imagine they have 50 customers and they are working, and we are talking here about 3 depots. So that's the first, that's the second and third. And they want to be able to find the best way to deliver all of these customers and the best use of these 3 depots. They're dividing the customers per depot. So the first depot would deliver the 18 first customers, the second one 15, and the last one 17. And so each one could be solved during QAOA or VQA. And so that's one last slide from Juliana's presentation. Again, Juliana, I know she's present here attending this webinar. Thank you so much for giving us this opportunity to show some of the very beautiful work that you're doing. And by the way, you should follow Juliana, because there will be a paper that will summarize all of these results that they've been working on for quite some time now. And that's just one glimpse actually of what something that I explained to you, a bit theoretical, and you can go through, test it with MIMIQ and using the different Jupyter notebooks. We have a client here at QPerfect that is trying to do the same thing. And actually, that's one of the things that we're trying to encourage, and what people should understand, in the sense that quantum computers hardware are maybe not perfect enough, and actually we'll see more in details why, but you can already do something today. There's already an optimization work to do. There's already a way to approach the problem and to find the best parameters that you can use. So thank you so much for following my side, let's say. As I said, I'll be able to send you the Jupyter notebooks by mail. And of course, if you have more questions, do not hesitate to either use the chat or to contact me by mail, of course. Okay, well, one last slide, even bigger zoom. Okay, and so this gets us to the question, what about real hardware actually? And so for this part, I'm happy to ask my colleague Tom to tell you more about it. Tom, can you hear us?
Hello, everyone. Can you hear me?
Yes, we can.
Yes, nice.
So what about real
hello,
hardware,
everyone.
Tom?
Yeah. I'm Tom, so I'm working in the research team here at QPERFECT. So I want to tell you a bit about another aspect of the work at QPERFECT that we are doing. So we are trying to bring your algorithm, so the applications that you are developing, into real hardware. And as you will see, there is a lot of work to do here. So yeah, if you can show the slide maybe, and the next one. All right. Okay, nice, thank you. So the idea is that now people are developing quantum computers, so QPU, so the real hardware. And over time, they are increasing a lot the available resources that you will have to run your algorithm. But it's not enough for the moment for a lot of algorithms like you saw here. So we need to do the simulation, but at one point you will want to run something on your quantum computer. So one effort that we are trying to do is to try to bring down the resources that you need for your algorithm. So this goes through trying to have more efficient algorithm, trying to have to find some other gates or that you can use, and in the idea of making hardware and software, so the application meet in the middle. So this is the one really important point to consider. For example, here you can see on the right, it is different points that consider different algorithms that are used to break the 2048-bit RSA. So this is an algorithm that is used to encrypt data. This is the standard that is used now. And as you have heard before, there is a quantum algorithm that has an exponential advantage compared to the classical algorithm in breaking this encryption. So each point represents a different algorithm, and you can see that they are plotted along the time, so the years, and you got on the y-axis the number of physical qubits, number of qubits that you will need in your quantum computers to run this algorithm. And you can see that indeed it's going down because people are putting a lot of effort to try to bring this number down to try to meet the hardware on the other side. But now there is another problem, is that you can see that the lowest one, like the most recent one, is still 10 to the 6, so 1 million qubits. This is already quite huge, as you can see on most of the algorithm that you are using, like it goes to 1,000 qubits usually. But here they estimate it at 1 million qubits. And so the question is, why is this requirement so high? And so this is the next part that we will explore. So if you can go to the next slide, to the previous one now. Yeah, thank you. So as we already explained before, quantum computers make a lot of mistakes because it is the problem of the hardware. It's just we operate on particles that are so small that it's really hard to manipulate the quantum realm without doing errors. So the best quantum computers that are developed today provide something like 0.1% of error, so an error each 1,000 operation. But to run your algorithm, you need some things like an error every billion or even quadrillion operation. Like here, you really need a really low error rate. So the question is, how do we do this? Is it just impossible to run something on a quantum computer? But no, it's not. What people are doing is to try to do quantum error correction. So trying to correct those errors that are coming into the quantum computers. So how is it done? The idea is that we take one of your qubits in the algorithm and we transform it into what is called a logical qubit. So a logical qubit will be an ensemble of qubits. So we'll take several physical qubits, we put them together, we make some operation, and then they represent just one logical qubit. And the magic thing about this is that this new logical qubit can correct error now. So for example, here on the bottom left, you have an example of what is called a rotated surface code. So it's a quantum error correction code that can correct up to one error in the processor. So now we can correct error, but we have the problem that for representing one of your qubits into your algorithm, we need many qubits into the quantum processor. And that's why there is this high overhead that we saw before, like 1,000,000 qubits to break RSA. And as you can see, it is a really costly part, and this is why we need a lot of optimization at this point. So the code that I showed you here is just one example among many. So there are a lot of codes that you can go through the error correction zoo that is on the bottom left, the link at the bottom right. So, and all those codes are all good candidates, but we need to search through them to try to find the best codes. And also when you have your codes, it is really hard to do gates now, because you cannot just do your gates like in your algorithm. You need to find clever ways to apply gates to those logical qubits. And the way you are doing those logical gates will cost more or less depending on what you choose. And so this is a really important part, and this is one of the work that we are doing at QPERFECT with the quantum logic unit is mapping your algorithm to a quantum error corrected algorithm. Or you also will heard about this term, it's the fault tolerant quantum computer. Quantum computation. So a computation that is tolerant to any error in the quantum processor. So now that we have this, we need to apply this to the quantum processor. So if you can go to the next slide. Yes, thank you. So what you see in the background is a real picture that has been taken into an experimental group where they have laid atoms into traps. So this is the atoms that will be used to do the real physical computation. Now we have a lot of atoms, so there they have like 6,000 atoms, but it's really early experiments for the moment. So we hope to have some more atoms in the future. But even with those 6,000 atoms, the question is how to use them the best. And it's not really straightforward, because when you see all those atoms, you have a lot of possibilities to do your algorithm on them. So one thing that you have to do is, and the method that we are trying to implement, is to try to divide our zone of work into some smaller zones. So we attribute some space for the storage, some space for the interaction, so where the gates will be performed, and some space where we are doing the measurements of the atoms. Now that we have this, we have to take those atoms and put them together to make the logical qubits that we have, and attribute which atoms will go to which logical qubits. And then it is really specific to this platform of using atoms, but we have also to schedule how we will move the atoms around into the different spaces. For example, if you have a logical qubit that is sitting in the storage zone and you want to measure it, you have to take it and move it around to the measurement zone, and then you can do the measurements. And of course, here you have all the problems of not having, you don't want any collisions, you want to have the path that is the fastest from one point to the other, etc. So you have to actually schedule in time also all those instructions. At QPERFECT, we are working with a partner, which is Access, which is an academic effort to try to build a neutral atom quantum computer. So quantum computers that use atoms to compute. And we are trying to develop this quantum logic unit that I told you before, that we will, and first step, do the quantum error correction. And second step, we'll try to use as best as possible the atoms that are provided by Access to make the computation. So now I have a little example for you. If we can go to the next slide. Yes. So here is a video of what the QUBO has done for a little circuit. So the circuit that you have on the top left. And the video here will show atoms moving around. And this has been compiled by our software. So it's just a really early experiment for our software. And you can see that each qubit in our GRZ circuit has been turned into patches of qubits, so a lot of physical qubits. And now those physical qubits have to be moved around. You have different zones. So on top, the reloading zone, on left is the storage zone, on right is the measurement zone, and in the middle, the interaction. And so you have to move around your qubits to make the operation, and then to move them to the measurement zone to measure them. So the additional qubit that you saw also, because there are not only 2 patches, but a lot more, those additional qubits are to detect errors. Those are called the ancilla qubits that are used to detect the errors into your data qubits, so the qubits that represent actual qubits in your algorithm. So yeah, this is what we are currently trying to research at QPERFECT, and we hope to have a good software quickly. And yeah, we already have this presentation here. Yeah.
Thank you so much, Tom. That's very interesting. I'm sorry, I think I lost my... Oh, yep, I lost my presentation. 1 minute, please. Now it's back. Well, thank you so much, Tom, for your insight. That's...
Just seeing a question, but
yes.
time to...
Yes, that was my point, actually. We're getting to the end of this presentation, so please, if you have questions, do not hesitate to ask. All of us are here for you. And of course, if you have extra questions or if you would love to book a demo, considering your MIMIQ credentials are only available up until Monday, do not hesitate to scan the QR code to reach out easily. So if you have questions...
So I can see maybe a question for the error correction. I can try to answer from Frederic. So the question is this because one error propagates through all the qubits? So I suppose you mean in one logical qubit. No, the idea is that the additional qubit that you have provides redundancy in your data. So all the qubits will encode each the same data. It's like, in a simple way, it's like you are repeating your data several times. So if you have an error on one of the data, you still have all the others that contains the true data. So you can retrieve the true data at the end.
I can see another question from Bogdan. Is the MIMIQ cloud on the public market so that, for instance, we can pay from a CNRS lab to use it? I mean, MIMIQ is on the cloud. You can either ask us directly, and we have licenses, or for organization, we also have like an on-premise version or a big license for organization, or you can access MIMIQ through the cloud using OVH, for instance. And we have another partner in Asia, SDT, but not necessarily. I mean, you don't have access from the CNRS. Yeah, so will MIMIQ support GPU-based simulation in the future? I think maybe Maxime can answer this one. I think your microphone is off.
Yes, sorry. Yeah, actually the current local simulator for the state vector already supports one GPU node. So I did not show it particularly, but the MIMIQ IDE was actually using Quantum, which is a local state vector simulator. And using this, you can use one GPU to run your simulations. We do not support yet GPU for the MPS-based simulations because it seems that MPS is less designed to make a full use of a GPU. It has some drawbacks from using the parallelization of the GPU. But for the state vector, yes, it is already for free, by the way.
Yes, maybe it's interesting to re-say that, but I think you've received some notebooks using Quantum state vector. So it uses your own device CPU or GPU. So you can test it. You can have it for free. You can download it with pip install Quantum, and it states vectors. It scales as much as your hardware can. So usually, let's say, optimistically speaking, up to 30 qubits, 32 max. Perfect. Well, thank you so much, everyone. Thank you for attending. Thank you for your questions and your interest. Please do not hesitate to reach out to any of us. We'll be very happy to answer you. And I'll leave the floor back to TerraTech.
Thank you, Eman. Thank you, all the team of QPERFECT. It was really interesting, and I hope everyone enjoyed it as much as we did. So that was a great second session of Quantum in Practice. You will be able to watch the replay soon on our YouTube channel. I will put the link in the chat soon. Thank you, everyone, and hope to see you soon. Bye.